Let's talk about projectiles. So if I have a coordinate plane and have a projectile launcher here at the origin and launch a projectile, in two-dimensional motion it will go up and out. Continue that down. And so let's talk about what happens to the projectile at each point along the way. So first, it is launched at a specific angle, theta. And that is its initial angle, so we're going to say it's theta naught. It has an initial velocity, v naught. And remember, we were talking about resultants and components. So v naught is actually a resultant vector. The component vectors would then be the vertical. So I'm going to say that's vy initial, and the horizontal, and that is vx initial. So as the projectile moves, we can use these vectors to describe the motion. So we already know from when we talked about freely falling objects that up here at the peak, the velocity actually will only be in the x direction because vy is equal to 0. This would be the same as if I were standing on something, threw something up in the air, and then it came back down, and if I were neglecting that horizontal displacement, remember the peak velocity here is equal to 0. So same thing in a two-dimensional system, the velocity at the peak in the y direction will be 0. That means that all of the velocity of the object will be in the x direction. So that's something super important to know about a projectile. So Vx is equal to the total velocity at the peak of this system. And what's even cooler than knowing that the horizontal velocity is the only velocity that we consider here at the peak is that the horizontal velocity throughout the projectile's entire motion stays the same. Same for the whole motion. So that's really cool. Any point along this path, if we have a point, say, part way up, at any point along the curve, we could say that here's my resultant velocity. This horizontal velocity is going to be the same as the initial horizontal velocity. So that's pretty awesome. And we don't know the vertical component of the velocity, or the y component of the velocity. Sorry, that kind of looks like a G. But this information is extremely helpful to figure out the total velocity, the components of the velocity, how far the object will go, how fast it'll go. If you know the angle and you know the distance, then you can figure out the velocity. If you know the velocity and the angle, you can figure out how high it's going to go and how far it's going to go. So this is extremely useful, and we can use our kinematic equations. So let's use trig first to talk about the components. So let me give myself some more space here. Ooh. Let me. Okay. So if we talk about this group in terms of the resultant and its components, we can think of this more like a triangle. So kind of rearrange it to have our resultant velocity vector, our horizontal velocity component, and our vertical velocity component. By looking at this, we know if this is our angle and this is 90 degrees, that means that our resultant is our hypotenuse. Our vertical component is our opposite, and our horizontal component is our adjacent. So we can find out each component of velocity if we just know the total resultant velocity by using trigonometry. So if we have Vx initial is equal to V naught cosine, theta. So remember SOHCAHTOA, we utilize the initial resultant velocity and our angle to find our horizontal component. Same thing with our vertical component. Our initial vertical component of velocity is just the initial resultant velocity times sine theta. So now let's consider the vertical motion, or the y motion. Because this object has constant acceleration, we can utilize the information that we know about those freely falling objects. So we're going to say that we have gravity. Don't forget gravity. Acting on this object as it falls, and that's in the negative direction. So we can use our kinematic equations and just talk about the y, or vertical direction. So remember, we have our kinematic equations. V equals V naught minus AT, or plus AT, but in this case we have minus AT because our acceleration is in the negative direction. Well, we can say, or we can use this equation for the vertical direction. So we can say Vy equals Vy naught minus GT. So that's kind of cool. Our other kinematic equations we can also use. We can say that y equals Vy naught t minus 1/2 GT squared. Oops, that should be a squared up there. And our last one, Vy squared equals Vy naught squared minus 2GY. So this right here says 2GY, so I kind of got squished there. But this information should help you approach some projectile motion problems. So a problem-solving strategy to help you would be to select a coordinate system like we did here, resolve the initial velocity vector into x and y components, so that's what we did down here, treat the horizontal motion and vertical motion independently, so keep them separate during your calculations. Follow the techniques for solving problems with constant velocity and analyze the horizontal motion of the projectile. So remember this and that little hint that I had there for a while. The horizontal velocity remains constant throughout the whole motion of the projectile, so you can use that to your advantage. Also, follow the techniques for solving problems with constant acceleration, so that's where this guy comes into play, to analyze the vertical motion of the projectile. And you'll need to use these kinematic equations that just talk about the y direction to solve these kind of problems.